Hello, these are the solutions to AP Physics C suggested problem set number 7.2, the minimum suggested problems. The first of these is problem 9.28, which has four small spheres of 0.2 kilograms each that you can regard as a point mass, so we'll go ahead and highlight that, as a point mass, that are arranged in this square that has 0.4 meters per side. So they are connected by extremely light rods, which means we can ignore the mass of the rods. And we want to find the moment of inertia about the system for several different axes. The first of these axes is an axis through the center of the square. So it's actually going into the page or out of the page, regardless of how you want to think about it, that is where it is. And so all four of these spheres are the same distance away from this axis of rotation. So for part A, I want to know how far away each of these masses is from point O. So the radius of this is going to be from a triangle. So this triangle is right here. And so if I have a triangle, I'll just go ahead and sketch one over here, where so one complete side here is 0.4 meters, which means that one side of the triangle here is 0.2 meters, and this is 0.2 meters, which means that this r right here is going to be the square root of 0.2 squared plus 0.2 squared. And so that means that the radial distance from point O, or the axis at O, up to one of these masses is approximately 0.2828 is what we'll say. So 0.2828 meters. Now that I know that distance, the reason I needed it was because in order to find the moment of inertia about point or an axis at O, I need to sum up all of the point mass moments of inertia. So for this particular instance, I will have 4 different masses. Now they are all the same distance, which is just a straight line distance. It's squared. It doesn't matter what direction it is. It just matters how far it is. And they all have the same mass. So I can say that this is simply 4 times my mass times my radial distance squared. So for us, this moment of inertia will work out to be 4 times the mass of each of these point masses, which is 0.2 kilograms, times this radial distance I found previously, 0.2828 squared. So the moment of inertia about an axis through O is 0.064, and then the units will be kilograms times meters squared, because I have a mass, which was given in kilograms, times a distance given in meters. So that's it for part A. Now for part B, it asks us to find our moment of inertia about an axis that is this AB. So this right here is my axis for part B. So I'm going to call this IAB, and again it is the sum of the point mass moments of inertia here. And so I need to know how far away these masses are from this axis of rotation. So I need this distance in all 4 cases. So that's actually pretty easy. That's just 0.2. So r in all 4 cases is equal to 0.2 meters. So in this case, all I need is the fact that there are 4 masses of the same mass located the same distance away from this axis. It does not matter if they are located at the exact same point as long as we know how far they are away from the axis of rotation. So my moment of inertia then is just 4 times the mass times this new radius. So actually I'm going to call this radius B. We'll go back and we'll call this radius A. Maybe lowercase a. So for this particular instance, we have radius B squared. So substituting here, my moment of inertia about this axis through AB is 4 times my 0.2 kilograms times my radius from that axis of 0.2 meters squared. So this moment of inertia will work out to be 0.032 kilograms meters squared. So that makes sense. We have a smaller distance from the axis of rotation to all of our point masses. Now, for part C, we have an axis that goes from the upper left sphere to the lower right sphere through point O. So I have an axis, that goes something, can't draw a straight line right now, something like this. So this is part C's axis. So in this case, I have two masses that actually lie on the axis of rotation. And since they are point masses, those don't actually contribute to a moment of inertia. So point masses on the axis of rotation do not contribute to the moment of inertia. So that means that the moment of inertia about what we'll call just C, or axis C, is the sum of the other two point masses' contributions. And so we have these two masses, and those two masses, as we found in part A, are 0.2828 meters from this center line. And that is the shortest distance that they will be from this axis at, or I guess we'll call it axis C again. So this is just going to be two different masses times this radial distance C, and radial distance C is equal to radial distance A that we found earlier. So moment of inertia about C is going to be 2 times 0.2 kilograms times the 0.2828 that we found in part A. So the moment of inertia here about this axis C that we created is also about 0.032 kilograms meters squared. So interpretation of this just tells us that it is approximately the same difficulty rotating this truss, this system of point masses, about an axis through C as it is rotating it about an axis through AB here. Question 9.29 is simply some practice calculating the moments of inertia of several objects. So for part A, we're calculating the moments of inertia for a thin rod with a certain length. So I'm going to go ahead and sketch this thin rod. All right, there's a thin rod. It has a mass of, let me write this in a different spot, a mass of 2.5 kilograms, and it has a length, so we'll call this a length L, of 75 centimeters. Now I'm going to go ahead and turn this into meters. So that'll be 0.75 meters. Simply because I know that I'm probably going to want my moments of inertia to be in kilogram meters squared. So I'm going to want the length, or the distance here in meters. So part 1, we'll go ahead and use some different colors to color code this. Part 1 is calculating the moment of inertia about an axis at one end. From the table in our textbook, we see that the formula for the moment of inertia of a slender rod about an axis at one end of the rod is 1/3 ml squared. So the moment of inertia, we'll call this I, is equal to, in this case, 1/3 times the mass of the rod, which is 2.5 kilograms, times the length of the rod, which we converted to be 0.75 meters squared. So the moment of inertia for this particular instance of the rod about one of its ends is going to be rounded to 0.469 kilograms meters squared. So there is our first simple calculation. Moving on, part 2 of this says through an axis about its center. So we're color coding this. So part 2 says we have an axis about its center. So I from our table gives us a formula of 1/12 ml squared. So this is much smaller than at the end, or than the axis at the end. So calculating this, our moment of inertia would be 1/12 times 2.5 times 0.75 meters squared. So So calculating this, we end up with a moment of inertia about its center of approximately 0.117 kilograms meters squared. So that is much smaller than the first part. Now finally, part 3 is about an axis parallel to the rod and passing through it. So parallel to the rod and passing through it is just right down the center of the rod. So since it's a slender rod that doesn't really have anything, how do we go about doing this? Well, we don't know the thickness of the rod, so for this particular case, we really can't say that it has any moment of inertia at all. So unless we specify the thickness, we cannot actually calculate a moment of inertia. So we must assume that it's thin enough that it really takes no effort to rotate about this axis. So now, moving on to part B. For part B, we'll start over our color scheme here. We have a sphere. So let's go ahead and sketch a quick sphere. So here's an outer edge. Here is a back edge. And so the mass of this sphere is 3 kilograms, and it has a diameter, I'm just going to go ahead and write diameter, of 38 centimeters. So we'll go ahead and say this is 0.38 meters, and this tells us as well that the radius will be half that, or 0.19 meters. So for part 1 of B, we have an axis of rotation through its center. Now, the first part is that the sphere is solid. So just an axis through its center. It doesn't matter which way you go through the center, it's symmetric. So my center is right here. And for a solid sphere, so I'll call this I solid sphere, we have a formula from our textbook of 2/5 mr squared. So I'm going to go ahead and just plug in the numbers that I have for the mass and the radius. So I have 2/5 times the mass of this, 3 kilograms, times the radius of 0.19, square it, and the moment of inertia of a solid sphere with these dimensions is 0.0433 kilograms meters squared. So there is my part I. Moving on to part II, for part B, it says now we have a thin-walled hollow shell. So we're just going to call this I hollow shell. From our textbook, the formula for this is actually 2/3 mr squared. Now, comparison here says this is bigger than the solid sphere. And the reason for that is all of the mass is concentrated at the radial distance from the center. So the moment of inertia for our hollow sphere with the same mass and the same dimensions is going to be 2/3 times 3 kilograms times 0.19 squared. And this hollow sphere will have a moment of inertia of 0.0722 kilograms meters squared. And that's it for part B. Now for part C, we have an 8 kilogram cylinder. So I'm going to sketch a quick cylinder. So it has ends. I won't worry about the rest of it. The mass of this cylinder is 8 kilograms. It has a length, so we'll say L equals 19.5 centimeters. And it has a diameter, maybe we'll write that below it, a diameter of 12 centimeters. So we'll go ahead and convert these to meters. So this would be 0.195 meters, and this would be 0.12 meters. And now we want to find the moments of inertia about the central axis. So for both cases, we're going to have a moment of inertia about this axis through its center. If the cylinder is thin-walled and hollow, and then 2 if it is solid. So first part, we have a hollow cylinder, so I'll call it HC. And from our textbook, the thin-walled hollow cylinder has a moment of inertia of just mr squared. So this is really easy to calculate. I just need to go back and find my radius. So if this is my diameter of 0.12 meters, then my radius is going to be 0.06 meters. So I will plug in that my mass is 8 kilograms and my radius is 0.06 meters. Squaring it, we end up with a moment of inertia for the hollow cylinder of 0.0288 kilograms meters squared. And then the last part 2, is if the cylinder is solid. So for a solid cylinder, my moment of inertia is 1/2 mr squared. So again, I'm just going to substitute in my mass and my radius. So my mass is 8 kilograms, my radius is 0.06. And I see that for a solid cylinder, my moment of inertia will be 0.0144. So you may be asking, why did we go and do all of this? It seems very easy. The simple answer is we need some exposure to just simply using these formulas to calculate moments of inertia for some common shapes, geometries, volumes, etc. Similarly, you can get a handle, or a little better handle, on how these different objects can have a different moment of inertia based off of if it is solid, hollow, or has a different axis of rotation. So for question 9.39, we have something called a flywheel for a gasoline engine. So a flywheel is simply just a wheel, as it says, that is rotating. And so we use some gears, mechanical advantage or whatever, to give a large amount of energy to my flywheel. And it has very low friction. So it tends to keep energy very well that can then be used, again, by gears if we want to extract that energy from the wheel. So the flywheel of a gasoline engine is required to give up 500 joules of kinetic energy while its angular velocity decreases from 650 revolutions per minute to 520 revolutions per minute. So first off, I'm going to record that K rotational here is 500 joules, or really the delta K rotational is equal to negative 500 joules. Right? I'm required to give up that amount of energy. So moving on from here, I have two different angular velocities. I have an angular velocity 1 of 650 revolutions per minute and an angular velocity 2 of 520 revolutions per minute. Now, looking at this, I actually know that I need to convert these to radians per second, and part of that is due to the fact that I have joules here. So joules are comprised, if you recall, of kilograms times meters squared per second squared. So my time must necessarily also be in seconds if I'm working with joules here. Then, as we learned previously, our revolutions also need to be in radians, because radians are the unit that can actually cancel out when we talk about using meters or linear distance. So in order to convert these, I'm just going to write it once because I'm doing the same conversion to both. I'm going to first convert revolutions to radians. So you would have 2 pi radians per revolution. And then I'm going to convert my minutes to seconds. So every minute contains 60 seconds. And so converting both of these, so I'm doing the same thing to both. My omega 1 will end up being 68.07 radians per second, and my omega 2 we'll call 54.45 radians per second. So these are my 2 moments of inertia. Now moving on to the second part, I have a change in kinetic energy of negative 500 joules. So I know that in this case, the change in kinetic energy for my wheel would be K2, or really K rotational 2, minus K rotational 1. So if I expand this, I will see that that is 1/2 times I times omega 2 squared minus 1/2 times I times omega 1 squared. And this is all equal to the delta K rotational that I recorded initially. So I can go ahead and factor out some things here. So if I factor this, I would have 1/2 I times omega 2 squared minus omega 1 squared. And so solving this whole equation for the moment of inertia, I would have 2 times k rotational over omega 2 squared minus omega 1 squared. So substitution here will give me my answer. So I have 2 times negative 500 over my final angular speed of 68.07 radians per second squared minus my, oh, I did this backward again. I knew I would do that. So 54.45 radians per second squared minus 68.07 radians per second squared. And see, I could have caught that even when I got to it because I knew that my moment of inertia must be positive. So if I end up with a negative moment of inertia, as I would have if I had put the larger number minus the smaller, dividing into a negative number, then I would have been able to notice that I had a negative moment of inertia. So I made some calculation mistake somewhere. Anyway, plugging this into our calculator, we get a moment of inertia for the flywheel of pretty much 0.6, and we'll go ahead and use 3 significant figures, 0.600, and this is going to be kilograms times meters squared. So, do not forget that when you are working with something in meters, you need to use radians for your angle. Do also not forget that if I have joules or something else in SI units, my time unit must also be in seconds. For question 9.42, we have a light flexible rope wrapped several times around a hollow cylinder. So I'm going to go ahead and sketch this up. So here's my hollow cylinder. And the hollow cylinder has a weight of 40 newtons, and it has a radius of 0.25 meters. And it rotates without friction about a fixed horizontal axis. So we're going to assume the axis is right in the middle. And it's attached to the axle by spokes with a negligible moment of inertia. So a spoke is just that cross part of a wheel. So these spokes don't contribute to my moment of inertia. It is solely due to the actual wheel part. So we can treat this as a hollow cylinder. And so we need to calculate the moment of inertia for my hollow cylinder. So first off, I know that from my table in the textbook, the moment of inertia for a hollow cylinder is just mr squared. Now this is one that you should be able to easily remember because all of the mass is located a distance r from my axis of rotation. Now, I have a radius, but I do not have a mass. So we need to reach all the way back to forces, where we know that weight is equal to mg. Therefore, the mass of this cylinder will be weight divided by g. In this case, 40 newtons divided by, we'll go ahead and use 9.8 meters per, or we'll go ahead and use newtons per kilogram, actually. And so our mass for this cylinder is 4.08 kilograms. If you use 4 kilograms, that's fine as well. That's what you should do probably on the AP exam. And anyway, now we can go in and calculate the moment of inertia for this hollow cylinder, which is 4.08 kilograms times 0.25 meters squared. So this moment of inertia ends up being 0.255 kilograms meters squared. Okay, now the remainder of the setup here is that this rope is wrapped around the cylinder, and we pull the free end of the rope with some constant force P. So we'll just sketch a rope going off to the side, and we're pulling with some constant force P for a distance of 5 meters. So I will indicate that I have moved a distance of, actually let's call it S, of 5 meters. At which point the end of the rope is moving at 6 meters per second. So we have a couple other things. It starts initially at rest. So omega initial, omega naught is 0, which also implies that the speed of the rope initially is 0. After I've pulled 5 meters, the final speed of the rope is 6 meters per second. So if there is no slipping, what is the force P? So I'm looking for P out of all of this. I might change colors here. So what is P? Now, in order to get to all of this, I have a moment of inertia, I have a distance, I have some force involved. So I know one of the first things I'm going to need to do is integrate work into this. So I know that work done is going to be equal to force times a distance times the cosine of theta. And in this particular case, I know that work is connected to the change in kinetic energy of my system. So since the rope is light, it does not have any real mass that we can speak of. So all of the kinetic energy, we'll assume, is tied up in the change in kinetic energy that is rotational for my cylinder. So going one more step here, this k rotational final minus k rotational initial is all I'm going to be worried about. And I know that the cosine of theta in this case is 1 because the force is in the same direction as motion. And I know that my initial rotational energy is 0 because of my initial angular speed of 0. So this will simplify to be just Fd equals k rotational 2, which will be 1/2 I omega, we'll just call it omega final, squared. So this P, I'm sorry, I wrote it as F, it should be now P, is going to be equal to I omega squared over 2 times the distance that the rope has pulled. So I have all 3 things that I need in order to calculate P. So I'll go ahead and start substituting. So the moment of inertia I found was 0.255 kilograms meters squared. My omega, oh wait, I don't have omega. So I need to go in and I need to find this omega. So how do I end up doing that? Well, I need some other relationship in order to find it. So thanks to the fact that this is a winding problem, I know that V is equal to R times omega for my cylinder. So in this case, if I want omega, I need to find V over R. Or really, this is V tangential. But in this case, V is the same thing. So my omega will end up being the 6 meters per second over my 0.25 meters. So the actual omega for this ends up being 24 radians per second. So I can take this back and plug it in. So I have 24 radians per second. Square that over 2 times the 5 meters that I've pulled. And so force P in this case ends up being approximately 14.7 newtons. Now if we want to spend a moment and look at units, we can. We have kilograms meters squared for moment of inertia times radians over seconds squared over meters. So I'll see that meters, one of those cancel. I know that radians will vanish, and I'm left with kilograms times meters per second squared, which is a newton. So this works out to be the correct units, therefore I have pretty good confidence in my problem solving. So again, unwinding problems hinge on this fact that I almost forgot myself, that the linear speed of whatever rope I'm pulling on or is moving is really directly related to the angular speed of whatever is rotating. Question 9.48 asks us to find the moment of inertia of a hoop, which is a thin-walled hollow ring or thin-walled hollow cylinder, with a mass m and radius r about an axis perpendicular to the hoop's plane at an edge. So if this is my hoop, so it's just a hollow cylinder, normally I know that the moment of inertia about this point right in the middle is simply mr squared. So I know that if I move this axis, which is at the center, over to one side and put it at the edge of the hoop, it doesn't matter really where, I'm actually needing to move my moment of inertia to a parallel axis. So this is where I want to use the parallel axis theorem. So the moment of inertia about the parallel axis is equal to the moment of inertia about the center of the mass plus mr squared. So in this case, my moment of inertia will start off with this moment of inertia, mr squared, and I will move it some distance. Well, this distance is equal to the radius of the circle, so mass is still m, and my r is still just big R. So my moment of inertia about this parallel axis is quite simply 2mr squared. So what does this mean? Well, it is twice as hard to rotate my hoop about an axis on its edge as it is about its center. For question 9.54, we're asked to use equation 9.2 to calculate the moment of inertia of a slender, uniform rod with a certain mass and length about an axis at one end perpendicular to the rod. So my rod looks like this, my axis of rotation is at the end, and so we're going to use equation 9.20, which is the integral definition of a moment of inertia. So r squared dm. So to set this up, I know that this entire rod has a mass to length ratio of m over L, and I know that that would be uniform throughout the rod. So any incremental change in mass is going to be proportional to some incremental change in, well, we can call it L or we can call it x. Let's call it x in this case. So if this is my x-axis, we're moving some distance x along my rod. Now, what does that do for us? Well, that tells us that dm, in this case, is equal to m over L dx. So if you notice, I'm not using rho for density here. I'm just simply using my mass to length ratio. So what I can do with this is I can go up here and I can say, all right, r, in this case, is my radial distance from this axis of rotation. So for this particular case, since my rod is perpendicular to the axis, then my r is actually equivalent to x. Now, the reason that there's a distinction here is that this point we're going to call the origin of my system, and then we are going to move out some distance L at the end. So my moment of inertia in integral form becomes the integral from 0 to L of x squared, and then I'm going to replace my dm with this m over L dx. So a little simplification here brings us to pull the m and the L out, since those are constant, and I have the integral from 0 to L of x squared dx. So what do we do from here? All we need to do now is integrate. So I have my constants, m over L, and then integrating x squared dx would give me 1/3 x cubed evaluated from 0 to L, which for us is pretty simple. So we have m over L times, in this case it'll be 1/3 times L cubed minus 0, so we'll just leave that off. And so I see that one of my L's cancels, leaving me with just the moment of inertia of 1/3 ml squared. So if I actually go into my textbook, I will see that that is the self-same moment of inertia for an axis at the end of a slender uniform rod. So the difference here from what we've done in class tends to be that we don't have a rho in this case. We just went straight to saying that the ratio is m over L, and m over L is a constant. So this is perfectly acceptable and sometimes even easier to do as far as dealing with density in my integrations. Question 9.75 is a rather involved linked mass question. So it's similar to what we've done before, where we have a mass on a table linked to a mass over a pulley. And the difference now is that the pulley itself has a moment of inertia. So there is some amount of energy that is associated with the pulley accelerating or rotationally accelerating. So to work through this, we need to figure out from energy how this entire system will work. So we're given that there is a coefficient of kinetic friction between the tabletop and block A, and we know that block B will descend some distance. So we're actually going to start by looking at energy and see if we need to even consider the fact that there is some friction, but we'll see. So let's start with our large statement of the conservation of energy. So we have K1, let me write a little more cleanly here. We have K1 plus K1 rotational plus UG1 plus UE1 plus work done by outside forces or non-conservative forces is equal to K2 plus K2 rotational plus UG2 plus UE2. Now let's go ahead and say what starts at 0. So we know that the system is released from rest, so that means that kinetic energy 1 is 0, and kinetic energy rotational 1 is 0. We also know that there is no elastic potential energy in any of our systems here. Then we know after some time that our kinetic energies will be non-zero, both K2 and K2 rotational, and we know that we will have changed some gravitational potential energy. So I have some gravitational potential energy initially, and I will have some finally. So we're going to look at the difference in those two at some point to figure out the distance d. And then finally, there is no elastic potential energy. Now, there is some work done by other forces because we have this friction going on here. And so we're going to need to consider some work done by other forces. So let's go ahead and see if we can expand this a little bit. So the gravitational potential energy for A will not be changing. So that means gravitational potential energy is only dependent on mass B's vertical motion. So I can rewrite UG1 as mass B times G times H1, its initial height. Then I can talk about the work done by other forces. Well, I need to know what the force of friction is on this object. So for block A, we're going to need to draw a free body diagram. I have a normal force, not going down. I have a gravitational force pulling down, which is equal to mass A times G. And then I have a normal force pushing up. And I actually know that the normal force and the gravitational force will be equal to each other from simple Newton's second law application. And then I have some force pulling to the right, and then I have some friction force pulling to the left. Now this friction force is the one that I'm interested in. The friction force is going to be equal to mu k times the normal force. And since the normal force is going to be equal to the force of gravity, that means that my force of friction is going to be mu k times ma times g. So how do I get from this force of friction to the work? Well, I know that if it has gone through some distance, that this is going to be equal to the force, but it's acting in the negative direction of the distance, so negative mu k ma times g. So there's my force, times the distance d. So this is the work done by my friction force, and it's negative because it's pulling energy out of my system. So then moving on, K2 will be the kinetic energy of translation here. So that'll be both mass A and mass B moving. So what I can actually do is I can actually say 1/2 times, we'll go ahead and say mass A plus mass B times their combined speeds, we'll just call that V squared. So this is my translational kinetic energy. My rotational kinetic energy will come purely from the pulleys, moment of inertia. So this will be 1/2 I times omega squared. And we'll deal with omega in a moment. Finally, we have the new gravitational potential energy of block B, which is mass B times G times H2. So this is already looking a little bit like a mess, so let's see if we can clean up any of it. So we know that mass B is changing gravitational potential energy, and that this H1 and H2 are related to the distance that the blocks move. So how are they related? Well, I know that as I move down from H1 to H2, that this is equal to the distance. So which one is larger? Well, H1 minus H2, because H1 is larger, would be then equal to D. So if I subtract this term right here, I would have MB times G times H1 minus MB times G times H2, which I can factor out the mass and G and have H1 minus H2, which I can then replace with D. So I have MB times G times D. Now some other cleaning up that I can do is I can go ahead and get rid of these parentheses. So I have mu k times ma times g times d. And then this is equal to 1/2 my masses times just v squared plus 1/2 my moment of inertia times omega squared. So what do I need to do now? Well, I need to figure out what I can do with this velocity or this speed and this angular speed. So I'm looking for speed of block B as a function of distance. So I actually want to leave speed in here, but it says nothing about angular speed. So since I am moving over the pulley without slipping, so this is moving over without slipping, that means that V tangential is equal to R omega. Well, I don't really know tangential speed, but I do know that it is equal to my linear speed. So since the radius of the pulley is R, that means that my omega could be replaced by this linear speed over big R. So I'll go ahead and do that. So I'm going to skip down to this line. Actually, I'll write this right below it. So I have 1/2 I times V over big R squared. And so this ends up being 1/2 I V squared over R squared. So this whole line is going to be rather long, but it's okay. Minus mu k ma g d equals 1/2 ma plus mb times v squared plus this 1/2 iv squared over r squared. So I want speed in terms of d. So let's go ahead and do a little bit more simplification. So first off, I can multiply everything through by 2. Actually, first I'm going to factor out d here. So I have mb times g minus mu k ma times g. And all of this is times d. Or we'll put it right here. Then I can multiply through everything by 2 to get rid of these fractions. So now I have ma plus b times v squared plus iv squared over r squared. So that means I can actually factor out v squared. So v squared in this case will be equal to, not equal to, but v squared times ma plus mb plus I over r squared. Just double checking my math here, and that looks fine to me. So to wrap this up, we will just simply divide one side by this, and we see that, so we want speed as a function of distance. So we have something that's very gross here, but we're going to leave it with a squared. So v squared will be equal to 2 times mb, mass of b, g, minus mu k, ma times g, over mass of A plus mass of B plus the moment of inertia of the pulley over r squared, and all of this times d. So I have this big coefficient times d. So does this make sense? Absolutely. Let's look at it real quick. So each of these terms has some meaning. So this right here, mbg minus mu k mag, is the difference in forces pulling on the string, right? Or the net force really pulling on the string, because we have the weight of B minus the friction acting on A. So this is the net force on my string. This term right here is the resistance to motion, or really the resistance to the forces, right? We have mass and we have inertia, and moment of inertia over r squared, that gives the mass of the pulley. So this is all just mass. And so really we just have that the velocity is proportional to the distance, because we have some change in force over some amount of mass. And that makes sense. This makes some amount of sense. So I'm going to go ahead and leave it as v squared. If you want to put in a square root, you can, but this seems to be the most pretty that this could work out to be. So hopefully you made it through this long effort of working symbolically and came out the other side with a little bit of appreciation for how intricate this can be. So for question 9.77, I have two metal discs that are connected on one axle, and they rotate about a common axis through their center, and they have two different radii. So R1 is 2.5 centimeters, which I'll go ahead and rewrite as 0.025 meters, and an R2, which has a size of 0.05 meters, and then mass 1 is 0.8 kilograms, and mass 2 is 1.6 kilograms. Now, A asks for the total moment of inertia of the two disks. So the total moment of inertia of the two disks is really just the combination of their moments of inertia, since they're both about the exact same axis. Now, a disk is identical to a solid cylinder. So I'm going to use, either from memory or otherwise, the moment of inertia formula 1/2 mr squared for a solid cylinder. And for my total moment of inertia, I'll call it IT, that's going to be the sums of these moments of inertia. So that will be, in this case, 1/2 m1 r1 squared plus 1/2 m2 r2 squared. So my moment of inertia total ends up being 1/2 times 0.8 times 0.025 squared plus 1/2 times 1.6, pardon my handwriting, times 0.05 squared. So the total moment of inertia of these two disks put together will be 0.00225 kilograms meters squared. All right, so this is part A. I found the total moment of inertia of the two disks together. Now part B says a light string is wrapped around the edge of the smaller disk, and a 1.5 kilogram block is suspended from the free end of the string. If the block is released from rest at a distance of 2 meters above the floor, what is its speed just before striking the floor? So we're going to go through this considering it from the energy standpoint. So I have K1 plus K1 rotational plus UG1 plus UE1 plus work done by other stuff equals K2 plus K2 rotational plus UG2 plus UE2. Now, immediately I can get rid of the elastic potential energies. Then I can say they start from rest. So that means that both initial kinetic energies are 0. And then there's no mention of friction, so we'll get rid of the work done by other forces. And then right before it hits the ground means that the gravitational potential energy essentially goes to 0. So all that I'm left with is an initial gravitational potential energy and then 2 kinetic energies in the end. So expanding this, I have mgh is equal to, or mgh1 rather, is equal to 1/2 mv squared, or v2 squared, plus 1/2 I omega 2 squared. So in this particular case, my mass is 1.5 kilograms. My g, same always, h is 2 meters. Again, mass is the same. And then I have a v2 and an omega 2. Now I want to know the speed of the block. So that means I'm looking for v2. So this is what I'm looking for. So in order to figure this out, I need to use the fact that there is no slipping occurring. So that means that v tangential is equal to r omega. Now the trick is that in this case, since the string is wrapped around r1, that my v, or v2 in this case, is actually going to be equal to r1 times omega 2. Or omega 2 will be v2 over r1. So if I want to do this really quickly symbolically, I can. I probably need to since I'm solving for v2. So I'm going to multiply through by 2. So I have 2 mgh equals mv2 squared plus 1/2. Now I'll call this IT since it works together as one big moment of inertia, times v2 squared over r1 squared. So I'm going to factor out my v2 squared here. Actually, I guess I can get rid of these parentheses since I squared them already. So I have 2 mgh1 equals, factoring out v squared, or v2 squared, I have m plus oh, forgive me, this 1/2 is gone as well. M plus IT times, or not really times, over R1 squared. So my V2, in this case, my speed will be equal to 2 mgh1 over m plus I total over R1 squared. So now I can do some substitution and find the speed of the block right before it hits the ground. So we have 2 times the mass of the block, which is given to be 1.5 kilograms, times g, let's go ahead and use 10 since this is complicated enough, times my initial height of 2 meters, over, again, my mass of the block, which is 1.5 kilograms, plus the total moment of inertia that I found to be 0.00225, over the radius 1, which is 0.025, and don't forget to square that. And so I have this rather ugly looking thing. So when you put this in your calculator, be very careful because you have some nested multiplication division work. So going through all this, you find that your speed of the block right before impact is approximately 3.43 meters per second. Whew, that's a lot of work. Now, how does this change for C? We're repeating it, but instead of wrapping around the smaller disk, we wrap around the larger disk. So the only thing that changes from part B to part C is that instead of radius 1, we're going to be using radius 2. So V2 would be equal to R2 omega 2. Now, thankfully, I did this all symbolically. So what changes is that V2 will now be equal to the exact same setup, with the only change being that I'm using radius 2 instead of radius 1. So thankfully, I can just go ahead and write that as mgh1 over m plus I total over R2 squared. So my second velocity, when I substitute everything in, will be 2 times 1.5 times 10 times 2, my initial height, over 1.5 plus 0.00225 divided by my radius 2, which was 0.05. Don't forget to square that. And now this ugly thing works out to be a different speed of exactly 5 meters per second. So let's explain the difference here. So why is the final speed of the block greater when we wrap it around R2 rather than R1? So this is best explained by a concept we haven't actually covered yet, and it has to do with something called torque. So if you think about the most efficient way to get an object rotating, you want to apply a force as far away from the axis of rotation as possible. So think about opening a door. If you're opening a door, you tend not to push the door close to the hinge. You tend to push it as far away from the hinge as the handle. So why is the handle on that side? Well, I'm actually more easily able to get my object rotating if I'm applying a force further away from the axis of rotation. So for situation C, where we have our string wrapped around the larger radius, we're applying our force further away from the axis of rotation. And so what does that tell us? Well, it just tells us that when we have a string wrapped around a larger cylinder, that we will end up with a larger speed because we are actually more easily able to rotate that system, in addition to letting us accelerate linearly much faster.